Hello, I'm Omar Yaghi. I'm a professor at UC Berkeley Chemistry Department and the director of the Molecular Foundry at Berkeley Lab. I'm here to tell you the story of metal organic frameworks and get you interested in this new chemistry. It's been a dream of scientists to build structures, chemical structures, from molecular building blocks for quite some time. However, this idea has never really come to full fruition until the invention of metal organic frameworks. But one can see from early literature back in 1959 some examples that this idea of building large structures from well-defined building units could be established. And that is the example of the copper-1 adiponitrile diamond structures shown here, with copper ions linked together by rod-like links adiponitrile to make a framework that is based on one of the densest structures known, and that is diamond, except here, because of the length of the units, the structure is open. In fact, in this particular case, the openness of the structure results in interpenetration, thus preventing the space from being accessible. Many examples in the literature have been made since then. And when I became assistant professor at Arizona State University, I also entered the field by linking bipyridine with copper-1 to make similarly a diamond-like framework. Except upon attempts to exploit the porosity, in this case by exchanging the nitrates with other ions, we found that the structures were very frail and they collapsed. So we set out to find a new strategy for building rigid metal organic frameworks that can maintain their porosity even in the absence of any guests. And there, as an inorganic chemist by training, we found that in my group that the linking of simple links such as terephthalic acid, when it's deprotonated as terephthalate, links to copper-2 ions, in this particular case zinc-2 ions, to make a beautiful grid-like structure based on, now instead of single metal corners or intersections, multi-metal rigid clusters, and that did the trick. And that is that now, upon evacuation of the solvent molecules that filled the pores to make a porous structure, we found that they can take up gases such as nitrogen and carbon dioxide to give a typical type 1 isotherm. When I say typical, I mean typical of porous materials such as, in those days, the traditional porous materials such as zeolites that were known to be truly porous. So in fact, for the first time, we proved that MOFs can be made architecturally stable, and that molecules, small molecules like nitrogen and carbon dioxide, can diffuse in and out of the pores without the framework collapsing or changing its character. It was really an exciting time when we saw this behavior. However, we were a little disappointed because the surface area that was derived from those numbers was disappointingly low compared to what one would get from zeolites and mesoporous materials and porous carbon, the common porous materials at that time. So we set out to establish and develop this strategy to make three-dimensional structures that are based on the primitive cubic lattice. And here I'm showing a very nice rendering by Escher of the primitive cubic lattice. And here, from our point of view, this is constructed from six-way branching points that are linked together by what is called ditopic links. So as a chemist, this translates into terephthalate, a ditopic link, which is one of the main components of plastics, zinc oxide, the main component of sunscreen, would serve as these multi-metal joints to make a variety of extended structures. In this case, a specific one that we targeted was MOF5. We published in 1999, and it was a beginning of the MOF field because in MOF5, if one looks at the structure as a whole, it's an extended structure in which organic units are the struts and the inorganic units, or the multi-metal units, are the intersections, forming again a rigid architecture. The yellow balls in this figure indicate the space within which gas molecules and small molecules can reside. The pore opening here is on the order of 1 nanometer, and the internal pore is not very much larger than that. The surface area we found, surprisingly, was 2,900 meters square per gram. We were very excited about this value because it essentially exceeded the record for all porous materials known up to that point. Just to give you an idea, what does 2,900 meters square per gram mean? If I take a gram of this material and I spread it on a flat surface, I would cover an entire soccer field. That's the kind of space, or real estate, let's call it, available to pack gas molecules like hydrogen, natural gas, and carbon dioxide, which I will be mentioning shortly. However, something quite fundamental was uncovered soon thereafter, and that is that for this special structure, one can functionalize the organic units to make essentially pores with different functionalities. And also one can expand the pores so that you have increasingly larger pore openings. This was a major discovery because one can do both of those things without changing the underlying topology of the structure. And it meant we can design solid state structures, something that many scientists or science has been waiting for quite some time. With these results, it was very clear that not only MOFs hold a great promise for designing of structures from organic and inorganic units, but also they have answered a long time challenging objective, and that is how to design materials, extended structures of materials. So really we have essentially up to that point at hand materials that are highly crystalline and composed from a variety of organic links and inorganic units to make porous structures, highly porous structures, into which we believed we can compact gases that fill very large space like hydrogen and methane into these pores and make the ultimate nano fuel tanks. This video was really provided to me by our collaborators at BASF, who I will mention some of our joint work shortly, who have contributed tremendously to the scale-up of MOFs. But before that, this set off really a revolution in the design of structures, because now one can take a variety of organic molecules with a variety of branching points, both organic and inorganic, combine them using very simple solution chemistry to make crystalline materials that are MOFs. So right now, hundreds of groups around the world are practicing this chemistry, and it's one of the most fastest expanding fields of chemistry. Accordingly, after our initial publications, there was a lot of competition on who will achieve the highest surface area material. And so as you can see from this graph, MOFs in general exceed the traditional areas in surface area in their porosity, and many more have been made. We have held and lost the record over the years, and the most recent record is held by our colleagues at Northwestern University, who reported NU 110, a material not very much unlike some of the structures that I have shown you, except with longer links. Our union with and collaboration with BASF for the last 11 years has been quite fruitful, and very early on we figured out a way of scaling up MOFs beyond the milligram quantities that at the time we were using in the lab. And thanks to the foresight and initiative of BASF, now these materials can be made in ton quantities and shaped into variously shaped bodies for various applications such as catalysis, gas storage, and gas separation. A MOF material is not very much unlike baby powder. It's a microcrystalline white powder, as you can see here, and it can be shaped to suit the application in mind. Let's look at a typical MOF structure. We found from single crystal X-ray diffraction studies on gases within MOFs that everything you're looking at in a MOF structure, whether it is the multi-metal joints or the 6-membered rings or the edges, are all adsorptive sites. Essentially, one can say they're all parking spaces for gas molecules to be sitting on and compacted within the pores. Another very special thing about these structures is that they are very open. They have pores without walls, and it means that substrates, gases, and other molecules can move in and out of the pores with great facility, and the pores never really get clogged. So this, you can imagine, is a boon for applications such as catalysis and gas storage. This particular structure, MOF 200, was a record up to 2011. It has a surface area of 10,000 meters square per gram. The new record is about 11,000 or so meters square per gram. And that's probably the upper limit for surface area of such materials based on 6-membered rings. So now we are all set using this simple chemistry and our collaboration with BASF to scale up the MOFs. We're set to put these MOFs in automobiles. In this particular demonstration of the usefulness of MOFs, this Volkswagen automobile was equipped with a MOF tank and driven around the world 28,000 kilometers with the fuel supplied from the various locales without pre-purification. This experiment was to demonstrate that the MOF can survive the journey with contaminants, whether they are small particles from the air or contaminants, trace contaminants that might be in the natural gas supplied, such as sulfur contaminants and water, that the material at the end of this exercise turns out has lost only 10% of its porosity, a minute amount compared to the very large surface area that these MOFs have. Let me give you an example of why this is very exciting. The dotted line illustrates the amount of natural gas that would go in the fuel tank without the MOF. And the blue line is the amount of gas that would go in the fuel tank with the MOF in it. You can see very clearly that, let's say at 60 bar, you can store at least double the amount of natural gas in the fuel tank when the MOF is there, which means that the MOF is acting as we have expected to compact the gas molecules closer to each other than they are in the gas phase. This is very exciting because that means an automobile can travel double the distance before it has to refuel compared to today's technology. So this, in the next couple of years, more and more natural gas fueled cars with MOF tanks will be in the market. Another very interesting application concerns the binding of carbon dioxide from flue gas or from combustion gases from power plants. This is a very important application for the environment, and I think MOFs figure prominently in the solution to that challenge. Here you see a mixture of gases, methane and CO2, passing through a magnesium MOF material. And you see on the other side, methane coming out in pure form, while CO2 is held within the pores. This is the kind of selectivity that is needed in order to make a change in the current carbon emission equation. And that is, can we use this technology? Can we further develop this technology so that we can capture carbon dioxide before it reaches the atmosphere? In the next segment of my presentation, I would like to share with you an inspirational story. As you know, we do science for many reasons, and most of them are very good reasons, such as helping society with the various problems that it faces. But sometimes students in our laboratories remind us of why we do science. This story is about doing science for inspiration. For quite some time, the challenge has been in making porous crystals is how do you make progressively larger and larger pore opening. In all the MOFs I've discussed so far with you, relatively small molecules can go into the pores because the openings are not very large. They're on a nanometer scale. Could we make porous crystals, MOF crystals, that have openings as large as proteins, so that proteins can go in, and we can therefore develop the chemistry of proteins within the pores. Let's say we can operate on larger molecules and develop the chemistry of larger molecules within the pores of MOFs. Here we chose one member of the MOF family, which we have reported in 2005, MOF 74. MOF 74 is very special because the multi-metal units are rod-like units that assemble in hexagonal form, linked by this simple organic unit. It's a special structure because no matter how geometrically, no matter how long that link, that organic link is, it will not interpenetrate, let's say self-grow, and therefore close the opening. So we set out, in collaboration with Fraser Stoddard at the time at Northwestern, we set out to use progressively longer links and test whether MOFs could be made. It seems a daunting challenge because even I, who have been working with MOFs up to that point, for 15 years with MOFs or more, did not expect that we can go beyond 3 phenylene units or 4 phenylene units, and 5 phenylene units in a link would be exceptional achievement. So this is where the students and their determination makes a difference. So let me share with you the results of this experiment. This is the opening of MOF 74, the parent structure. And I'm indicating here the dimensions, 14 angstroms by 10 angstroms. And this is only with 1 phenylene units. But my students made 2 phenylene units, the same structure, but now the pores are 20 by 16. 3 phenylene units gave us 27 by 22. Now we are approaching the world record, 33 by 28, 4 phenylene units, 5 phenylene units, and we went on to 6, 7. 8 is missing for various reasons dealing with the synthesis of the link, but 9, and up to 11, 98 angstroms by 85 angstroms. That is the largest pore opening of any porous crystal known. Very exciting because a material made from such a long link really gives us a lot of ideas on where this chemistry can go. One idea is that the pore opening now, 282 atoms wide, can fit a protein as large as GFP, green fluorescent protein, without the protein being unfolded in the pore. In fact, in this particular example, the MOF with 6 phenylene units can fit such a large unit. We are still examining the chemistry of the largest members of this group. Another really major achievement here is that MOFs have always shown electron beam sensitivity. And so through my collaboration with Professor Osamu Terasaki, he has succeeded in observing through SEM and TEM the pores of MOFs. This is giving us a lot of ideas on the chemistry that happens around the opening of the pores. So where is MOF chemistry going? So in this final segment, I'd like to share with you just one experiment that has really made a huge difference in terms of carbon capture. In many chemistries, if you try to take multi-component synthesis, or let's say making a material from many different components, usually you get phase separation. With MOFs, you don't. We discovered that the MOF backbone forms regardless of what you have, what functionality you have on the link. And so, again, my students have taken these links, the same link but with different functionalities, and assembled them into one structure. What does this really mean? It means that this crystal of this, what we call MTV MOF, multivariate metal organic framework, that crystal, if you look in its pores, it has many different functional groups decorating the interior of the pores. What is the arrangement of these functional groups? How are they apportioned? These are new questions that really touch on big problems that have been facing the material science world. Recently, in a collaboration with Bernd Schmidt and Jeff Reimer at UC Berkeley, we have uncovered that these functionalities apportion themselves so that they map the space within the crystal with specific functionalities. In this graph, you see in the yellow domain is one functionality, the blue domain is a different functionality, and they're arranged in either large domains, small domains, random, or well mixed, depending on which functionalities we use. This kind of chemistry essentially results in, when you mix functionalities and you apportion them in the proper way, you find that we achieve 400% improvement in selectivity for carbon dioxide relative to the unapportioned or the unmixed material. So this is just one example of where the chemistry is going. But once you figured out how to take organic units and inorganic units, combine them together through strong bonds, there is absolutely no limit to what can be done. That is beginning to bear fruit as we speak. I encourage all of you to look into this chemistry, and I guarantee that you will have many different ideas. We call this chemistry reticular chemistry, linking building blocks through strong bonds to make extended structures. Thank you very much for your attention.